encounter in the heavy current industry. Now, when we basically look at the commercial machines, we have two types. Basically, one which is basically the stationary field type, and the second type is basically the revolving field. And the stationary field type basically looks like your DC machine. So it will have basically stationary salient poles that create your DC field, and basically you will have a revolving armature at the center, and obviously the conductors on your armature will basically cut through the magnetic field, and then obviously a current will be induced in those conductors. And the armature is basically connected via three-phase windings, okay, and it's connected to your slip rings, which is mounted on the shaft, and thereby it will basically pass through and go onto your load. So these first type, which is stationary field, the problem with these machines is they require a set of brushes which are sliding on slip rings, and that's enabling the armature to be connected to the external load. And the problem with those machines is it requires high maintenance, because obviously those brushes are subjected to wear and tear. So those stationary type machine, they basically we use them for ratings that are, as you can see, very low. It's 5 kVA output. So if we're using higher power, which is most likely that's what you're going to use in the electric power industry, then we basically move on to the next one, which is the revolving field type. So your revolving field synchronous generator, it's basically looking a little bit closer to what your induction, your three-phase induction machine looks like on the stator side. So it consists of a three-phase stationary armature, which is called the stator, right? And the three-phase stator winding is basically used to connect the load without going through large unreliable slip rings and brushes. So because we're using that stationary type, because the stator is basically now stationary, obviously then it is much easier to basically insulate your windings, right? So when you're sizing your insulation, it's basically easier. And secondly, they are not subject to wear and tear, and also centrifugal forces, because the stator is stationary, right? So just to show you how it looks like, I'm going to look at figure 1. So as you can see, figure 1 is showing you the cross-sectional view of a synchronous generator. So it consists of basically a main exciter part, right? And that's your three-phase stator here, and your rotor is basically mounted on the shaft of the machine, right? So the shaft is by your turbine. It can be a steam turbine or a hydro turbine, and that's basically receiving mechanical power, and it's rotating the shaft. And now, as you can see, your main exciter firstly is connected to this shaft, basically to generate the current that will be required, right, for your rotor field current, right? So this rotor field current is basically produced from the main exciter system, which is also extracting power from the main shaft, right? So the system is basically, you have a pilot, exciter, right, which produce the field on your main exciter, and then that the conductors that are connected to the, basically mounted on the exciter, is looking like a DC machine, right? It's connected to the commutator and slip ring, right? And from there, you're getting your DC current that's being fed to the rotor field circuit, right? So as you can see, the rating of your main exciter is basically around 2,400 kilowatt, right? And that's producing a field current of 6,000 amps that you require on your rotor side. This is for a large machine which is rated at 500 megawatt. And you can see the output voltage is 12 kilovolt, so that's medium voltage. And for the exciter system, it's rated at 2,400 kilowatt. And the pilot exciter is much lower rating, it's 25 kilowatt. It's basically feeding the current to the stator of the machine, and the armature then produces your current that's required for your rotor field current. Right, so if we go back to slide number 3, we will basically look at how many number of poles that your machine requires. So the number of poles on your synchronous generator is basically dependent on the speed of rotation of your machine and the frequency of the voltage it generates. So every time your complete pair of poles which crosses a conductor, so now we're talking about the north and south, when it basically crosses the conductor, the voltage that's induced basically goes through a complete cycle, and that frequency of the voltage is given by equation 1, and it's given by the product of P, which is the number of poles, times N, which is the speed of the rotor, right? And that's divided by 120, and that gives you the frequency of the induced voltage. So you will see that in the machines that we will look at in our tutorials or examples, there are two types of machines. In terms of frequency, you'll find that some machines are rated at 60 hertz. So these machines are more designed for the American power utility because they use 60 hertz. And the machines that are designed for South Africa or the African continent and the Europe, so basically they work on 50 hertz. And obviously then they will have different number of poles and speed to generate 50 hertz as compared to the 60 hertz machine. Right, so if we move to slide number 5, we will basically now focus on the stator of the machine, right? So the main features, we'll look at the main features of the stator of the machine. And as I mentioned earlier, the stator is basically consists of a 3-phase winding, right? That's basically very similar to your induction machine, and it's composed of cylindrical laminated core that contains a set of slots that carry a 3-phase lap winding, right? So that's what you've studied in your machines 1. It's and the stator winding is always connected in star for the generator, and neutral is grounded, right? So there are a couple of reasons why we basically connect it in star. The first one is, obviously, when you connect the machine in star, the voltage per phase is basically 1 over √3 times the line voltage. So that's basically 58% of your line voltage. So because the per phase voltage is lower than the line voltage, so that allows for firstly your amount of insulation. So the size of the insulation is reduced, right? And it allows for larger conductors because now you have more space. And if you have larger conductors, that translates to higher power rating or higher current, right? And the second reason why we connect it in star is the induced voltage in each phase normally gets distorted when the machine is loaded due to third harmonic voltage. So what happens when you have a star connection is this type of connection cancels the distorting line to neutral harmonics, and thus the distortion do not appear between the lines, right? If you have a delta connection, basically now what happens is the harmonic voltages will add up upon loading, and obviously then it will distort your output voltage. So that's the reason we use star connection for a generator on the stator side. Nominal line-to-line voltage for those generators, they're normally medium voltage, and maximum you will reach is 25 kilowatt, right? And then obviously for transmission, we step up the voltage from medium to extra high voltage or high voltage, and then we transmit the power to the distribution centers. The second features that we're going to look at is the rotor of the machine. So there are two types of rotor. You have what we call salient pole rotors, right, which are normally used for hydraulic turbines. They are normally low speed. And second type is your cylindrical rotors. Now for the machines that are hydraulic, their speed are normally lies between 50 RPM to 300 RPM, and obviously the frequency is set as either 50 Hertz, like we use in South Africa, or 60 Hertz that they use in America. So obviously, if you use equation 1, you can see that these machines, they require a much larger number of poles as compared to the second type, which is cylindrical rotors. So cylindrical rotor machines, they are driven by high-speed steam turbines. So they are basically smaller in size and more efficient as compared to hydraulic turbines. So because they have high speed, so obviously now from equation 1, you will require less number of poles on the machine. And obviously you need a minimum of 2 poles because you need a north and a south to basically produce your magnetic field. And that will be basically your lowest number of poles that you can use. The fourth section is looking at the field excitation and exciters that we use in synchronous machines. So basically they ensure a stable AC terminal voltage, right? So, remember the current that's basically passing in the rotor circuit is basically producing the magnetic field in the air gap, and that's sweeping your conductors on the stator side. And if you basically have a control system that's fitted on your excitation circuit, which is basically your main exciter circuit, that will basically enable you to vary the rotor current, field current, and that will allow you to basically hence vary the voltage that's being induced on your stator side, right? So by having this control circuit, we ensure that a stable voltage is maintained. by basically having a feedback control. And if there is, for example, sudden changes in load, or your machine is subjected to a fault on the system, then your exciter system will basically operate its control to try and counteract the effect of the change in load or the fault on the system to maintain the terminal voltage to its required value, right? So these exciters are designed to react very quickly to basically keep the terminal voltage constant. Now, with the development of power electronic technology, basically conventional DC excitation system, which are subjected to brush wear and tear, carbon dust needs to be cleaned and repaired regularly, and you need replacement of brushes, slip rings, and commutators. So all these problems basically have been solved with the use of power electronic technology, which now makes use of what we call brushless excitation systems, right? So if we'll go back to figure 2, so if you look at figure 2, this is employing a brushless exciter. So what it's using is, instead of having the commutator, slip ring, and brush system to convert the AC current to DC, now we've basically used a 3-phase bridge rectifier to convert the AC current to DC current, which is required for your rotor circuit, right? So we're using a power electronic rectifier to convert this current, and now we do no longer need this inefficient system, and this is more efficient and obviously less maintenance cost on your generator. So brushless excitation system is being used nowadays instead of this all technology, and obviously the main exciter now consists of a 3-phase stationary field generator whose AC output now is rectified by a bridge rectifier, and the DC output of the rectifier is fed directly to the rotor field winding. So if you look at the size of your generators, there are several factors that affect them. One is what we call the efficiency of the generator. So if you look at a power system, you will see that they employ what we call base generators, base load generators, which basically operate at 100% of the time until they go on service. So the base load generators, they since they are working 100% of the time, every percent increase in the efficiency translates to extra revenue for the power utility. So now, if you look at how when the size of the generator is changing, you will see that there is a major change in the efficiency. From 1 kilowatt, you're getting efficiency of like around 50%. And if it's a larger machine, which is 1,000 megawatt, you're getting an efficiency which is close to 99%. So with respect to efficiency, so obviously larger machines are favored as compared to lower size machine. However, basically we encounter limitations with regards to the cooling system when we use large machines. So large machines, they have high power losses per unit surface area. So that's in watt per meter squared. If your machine is rated below 50 megawatt, we employ what we call circulating cold air system. If it's basically rated between 50 megawatt to 300 megawatt, you can use hydrogen cooling. And if you are basically in the range of 1000 megawatt, you require hollow water-cooled conductors. So what happens as you increase the size, you can see the system for the cooling gets more expensive. And so ultimately the cost of the cooling exceeds the savings made elsewhere, right? Now, with regards to comparing this to speed, the low speed high hydraulic machine always bigger in size, obviously, as compared to high speed machines of equal power, right? So if you compare, for example, a 50 megawatt hydraulic machine to a 50 megawatt steam turbine, the hydraulic one will have a bigger size. That's because of the design of the turbine, which occupies a much larger surface area. Right. So we'll move to the next slide, which is slide number 11. So when we look at the excitation system of the machine, we basically, if you look at figure 3, so we're basically now interested in varying the excitation current and looking at how does the voltage of the machine response when we vary the excitation current Ix. So this is a two-pole machine, okay, cut in north and in south, and the field is basically connected is passing through the stator winding, and the three-phase winding ABC there, and the neutral is fitted there. And we basically measure the phase voltage. So from phase A and the neutral, we're basically measuring this voltage. And we're trying to produce what we call the no load saturation curve. So what we're doing is drive the machine at rated speed, right? And we slowly increase the excitation field current from 0, okay, to its rated value, okay. And obviously, as you can see, the terminals of the machine are on open circuit, so it's on no load. There's no load connected to the machine, and the field current, okay, produces the flux in the air gap, right? And as we increase the field current, what happens is you can see that the voltage induced between the line and the neutral there is start to increase as we increase the field current. Okay, so in the initial stage, as you increase the current from, for example, 0 to 100 amps here in this machine, which is rated at 36 MVA and 21 kV, right? So that's the three-phase power rating of the machine, and that's the line-to-line rating of the machine, right? So remember here we basically looking at E naught, which is your line to neutral, which is your phase voltage, and here is your field current Ix. Okay, so if you increase the current, you will see that the voltage E naught will start to increase, and at the initial stage, you can see it's rising linearly with the increase in the field current, right? And it will reach its nominal value at, as you can see here, 100 amps. You reach the rated value of the line to neutral voltage. So why are we getting 12? It's because that's 21 kV, that's line to line. You divide by √3, then you basically get a value of 12 here. So that's the nominal line to neutral voltage. So as we increase the current, we see the voltage increases, and now once we exceed this rated value, we see that now further increase in the current basically produces a smaller rate of increase in the voltage, right? So the gradient of the curve, as you can see, is decreasing, right? And this is due to what we call saturation of the ion core in the machine, right? So what happens is, as you keep on increasing the field current, right, the conductors and the ion core on the stator is getting saturated, okay? And as it gets saturated, you will basically require a much larger increase in Ix to give a very small increase in E naught, okay, due to the saturation of the ion core on the stator side. Right. If we look at the next slide, which is slide 13, right? So we basically start to look at the same machine, which is now basically showing you the three-phase representation of the same machine. And so what we were doing is we were looking at the line to neutral voltage between phase A and the neutral. And so we were focusing on only one phase, but remember there is three phases, so you will also have the B phase to the neutral, and you will have the C phase to the neutral, right? And remember that in this rotor, that's for now we're focusing on the phase A, which is producing the flux from the current, excitation current. So this rotor is also acting on phase B and phase C. So we'll have equivalent voltage being induced between B and N and C and N. Only difference is each of these voltages will have a phase difference of 120 degrees, right? Because of the spatial difference between the three-phase winding of phase A to B and C. So then you will basically have your 120-degree phase shift in between them. So this is basically the figure 5 is showing you the three-phase representation. And now if we connect the machine to a load, so we can basically then develop the equivalent circuit of the machine, right? So in this section 8, we will look at what is the synchronous reactance of a generator, okay, and also how can we derive the equivalence of the synchronous generator. So we will start with this figure 6, which is showing you a machine. Remember, it's got a shaft that's being driven by a turbine. And what's happening is you feeding a current, a field current to the rotor, and that interacts with the stator, and obviously then it induces voltages onto your three-phase terminal of the stator. And if you connect a load here, it will receive three-phase power. Right. So if we look at figure 7, so now that's showing you the machine that we looked at in figure 5, now connected to a three-phase load, which is connected in star, right? So you'll have phase A, phase B, and phase C, and they are all connected to each phase of the load. So that's your phase A, that's your phase B, and that's your phase C there, right? So both have a star connection, and the neutrals will have the same potential. So neutral N1 and N2 will have the same potential if the load is balanced, right? And then the load is balanced, there won't be any current flowing in this link here, which is your neutral, because they will have the same potential, right? If there is an unbalanced load, then obviously current will start to flow in this connection. Okay. In our course, we will basically only look at a balanced load. The unbalanced load systems, you will basically study that more in Power Systems 1. All right. As your field rotates, okay, so when the rotor turns here, the field flux phi will basically sweep through your stator winding and obviously induced a voltage E0 between phase A and the neutral. And each of the stator terminals, they will also get induced a voltage of magnitude E0, except that they will be out of phase by 120 degrees. Right. So the stator winding, as you can see, for each phase, it has basically obviously it's a coil, right? So it will have a certain inductance, which is represented by L, and obviously being a copper conductor, it will also consist of a certain resistance R. And basically now, because your inductor is represented in AC circuit, it will basically now translate into what we call an inductive reactance. And that's given by equation 2, which is basically 2 pi F times L. Right, so that's your what we call the synchronous reactance of the generator per phase. Right, so it's given by it's basically represented by XS, where S is representing synchronous, and that's X is representing the reactance. Right, so this is a very important parameter for the generator. Okay, because it is one of the main components in the equivalent circuit of a generator. And the resistance of the stator is normally much lower than the reactance of the generator. So typical value is that the synchronous reactance is 10 to 100 times the value of the stator resistance. And you will find that in most cases, the resistance can be neglected unless obviously you're doing efficiency or heating effects in your calculations. Then you'll need to basically include the resistance of the stator. Right. So this reactance is basically the reactance per phase. So each phase will have the same value, right? If you look at the next slide, which is slide 16, we are basically now trying to represent the electrical effect of the machine onto the stator side. So as we were discussing, the rotation of the rotor and the production of the field, the flux in the air gap due to the rotor current is basically inducing three-phase voltages into the stator circuit, and that's given by E0, magnitude E0. And as you can see, phase A will have, if we take it as the reference, it will have an angle of 0. Phase B will have an angle of minus 120 degrees, and phase C will have minus 240 degrees. Right, so it's inducing those three-phase voltages, and each phase of the stator will consist of two components in the circuit. One is the resistance of the stator, which is represented by R, and the reactance of the stator, which is represented by the synchronous reactance XS, right? So obviously, these circuit, as you can see, is connected to a three-phase load. So each of them will have their own current flowing. You'll have current IA, IB, and IC flowing onto the load. And basically, when we analyze synchronous machines, since if you, from your background of electrical machine 1, as you can see, when we analyze three-phase systems, we can basically simplify our analysis by doing the analysis per phase, right? So we simplify the circuit and consider only one phase, right? We do the analysis and then we convert back to three-phase. Okay, this is to simplify the calculations, because we know that the same, for example, power that's per phase, you can convert it to three-phase by multiplying by 3, and you can also convert your current per phase or your voltage per phase back to three-phase line voltage, depending on the type of connection if required. So figure 8 can be basically simplified into figure 9, where we will basically consider one phase. And you will see also we've removed the resistance for now, because we discussed that it can be neglected if it's very small as compared to the synchronous reactance. And that will basically now give you the equivalent circuit of a synchronous generator per phase. Now, this circuit is basically showing you the effect of the rotor, which is carrying the rotor excitation current, Ix, producing the flux, and that's basically determining the value of E naught, which is the induced voltage per phase. And in between the load and this induced voltage, you will have the synchronous reactance, which represents the reactance of the stator per phase, right? And the current that's passing here, that will be your load current. And the terminal voltage is known as E, is basically the voltage between terminal line to the neutral, right? So these parameters, you need to know them you need to be very precise. When we speak of E naught and E, there are two different voltages. One is the induced voltage and one is the terminal voltage, or you can also call it the load voltage, right? And the current obviously is connected in star, so the current that's passing in the stator is also the load current. Right, so now if you are required to convert your terminal voltage to line, obviously now you need to, if it's basically a star connection, you multiply by √3, you will get your line voltage, okay? And the current, again, if it's a star connected, so the line current is basically the phase current, okay, for a star connection. So that we can also convert, but it's going to be equal. So in most cases, we basically analyze the machine using this equivalent circuit. We will have cases where we will add the resistance to show the effect of the resistance of the stator on the equivalent circuit, and when we basically look at efficiency calculation of the generator and losses, so then we will include the resistance of the stator in the equivalent circuit. In the next section now, we will basically look at how can you determine the value of this synchronous reactance, okay? This is what the test that we do on the synchronous generator is basically two tests. One is the open circuit test, and the second one is the short circuit test. right? So we use those two tests to determine the value of the synchronous reactance of the machine. And there is another test we do to determine the resistance of the stator, right? So that test is also, you've done it, I think, in your machines one practical, where you use DC voltage. So it's called the DC test. You apply DC voltage to the terminal of 2 of the line, and you measure the DC current that's passing through the 2 lines, and then you can determine the resistance of the stator. Okay, so initially we will focus on the open circuit and short circuit test, and when we're doing the tutorials, we will also include the DC test to determine the resistance of the stator. Right, so in the first section, we will look at the open circuit test. So here what we do is we drive the generator at rated speed, right? And what we do is we slowly raise the current X, okay, from 0 until basically we can measure the rated line-to-line voltage across the basically the terminal, okay, and the corresponding current, excitation current, and the nominal voltage is recorded, obviously, where En is the line to neutral voltage. So here, if you're measuring it line to line, you'll have to convert by dividing by √3. But if you're measuring line to neutral, then you don't need to convert. The second test, which is the short circuit test, this is a little bit more, you need to require more safety precaution, because obviously you're applying a short circuit to the stator of the machine, right? So obviously it's dangerous, because high current will flow in the stator. So the initial precaution that you need to make sure is required is that you set your field current to 0 before you start the test, right? So again, you will drive your generator at rated speed, right? And you will gradually increase Ix, right, until you reach that nominal value Ixn, which you've measured from the open circuit there, right? The nominal value of your field current. And once you've reached that value of In, you will basically record what is the current, what is passing in the stator, right? So the short circuit current is measured, I short circuit, and to get the synchronous reactance per phase of the machine, you basically take En, which is the line to neutral voltage, you divide by the short circuit current, right? That will basically give you the reactance, synchronous reactance per phase of the generator, right? Just take note that the synchronous reactance of the generator is not constant, okay? It varies with the degree of saturation of the machine, right? So if your machine is getting saturated, what happens is the value of excess will basically will be lower, right? The more, if it's heavily saturated, for example, the synchronous reactance can be half of the unsaturated value. So we will look at examples of how can we determine those two values. One is the unsaturated synchronous reactance and one is the saturated reactance. We will look at that in one tutorial question, where we will look at a machine that's connected to a utility grid, and we will look at the open circuit characteristic and the short circuit characteristic of the machine, and we will basically use those characteristics to determine the saturated and the unsaturated value of the synchronous reactance. Right, so if you look at section 10, we will basically consider the per unit system for the machine, which is the synchronous generator. So that's going to be a bit similar to what you've studied back in your machines 1. To convert to per unit, what you require is your base values of your power and your voltage. So if you look at a synchronous machine, you look at the nameplate on the machine, it will give you basically the power rating, right? So that's normally your MVA or kVA rating, which is S. And you will also have what we call the line-to-line voltage of the machine. So you'll have those two values, right? So from those two values, you can basically work out your parameters in per unit by selecting those two base values and then converting basically your current, your voltage, and your power into per unit. So how you do that is you, for a synchronous generator, the rated line to neutral voltage is used as EB, right? So for example, if you're given the voltage of, for example, 12 kV, so that will be line to line. For you to get line to neutral, you need to divide by √3, and that will give you the base voltage. The three-phase power will be given in, for example, let's say if you're given 30 MVA and you want to work out the base power, so that will be your power rating, which is 30 MVA, which is three-phase. So you're converting to per phase, so you divide by √3. So 30 MVA, you divide by 3, you're gonna get 10 MVA, so that will be SB. So once you've worked out EB and SB, you can work out ZB. That will give you the base impedance, and that's given by EB squared divided by SB, right? So that's equation 4, and that will basically give you the parameters that you require for working out the all the parameters in per unit. Right. The other parameter that you may encounter in synchronous machines is what we call the short circuit ratio. So instead of expressing the synchronous reactance in per unit, sometimes you are given the short circuit ratio of the machine, right? So what it is basically the inverse of your synchronous reactance in per unit, right? So by taking 1 over XS in per unit, you will basically come up with what we call the short circuit ratio of the generator. All right, so I wanted to basically cover these 20 slides for today. I don't want to cover too much. I'd like if you can interact with me just to let me know if you have any questions. You will need to switch on your microphone. Right, so I see a question here. They've asked how the pracs will be done. So what we are working on is you're going to be given 2 practical assignments. So we won't be basically running the actual machine in the lab this semester. So You'll be given practical assignments to basically replace the labs, and you will basically work in groups and submit the practical assignments to basically replace your prac marks that you were normally doing for this semester. Right, so other question, slide needs to be uploaded 11 to 20. Yes, I'll do that right away. All right, so that I think was not enabled on the Moodle. Right, so that can be sorted. All right. Any other question? All right, so we'll end the lecture for today. The next lecture will be during our scheduled time on Friday. All right, so we'll meet you on Friday, and we'll continue with the next part of the lecture. Thank you very much, guys.